A church is located 10 miles east of a school and 5 miles south of a hospital. An engineering department is planning to construct a new road from this school to the hospital by restoring a section of an old road between the school and the church, and then only a section of this, and then joining it to a new road to the hospital. So if it cost $100,000 per mile, okay, for restoring this old road here, and it cost $300,000 per mile for constructing a new road, how much of this old road must be restored to minimize the construction cost? Now, let's represent this section to be 10 minus x. Actually, we can represent this by x, but I prefer it to be 10 minus x so that I can get a simpler expression for this length. So if I represent this to be 10 minus x, then this section here is equal to x because the distance between the school and the church is 10 miles. Okay, now what is our goal? We want to minimize the construction cost. So our goal is to minimize cost. And what is the construction cost here? So we need to find the cost for this section plus the cost for this new road. Since the cost for this section is $100,000 per mile and the cost for this new road is $300,000 per mile, then the total construction cost will be $100,000 times 10 minus x and then plus $300,000 times square root of 25 plus x squared. Now, what is the domain under consideration here for our variable x? It is clear from our diagram that x must be between 0 and 10, inclusive of the endpoint. So x is greater than or equal to 0 and less than or equal to 10. So x equals 0 means that the road will be constructed from S to C and then C to H. Now, what does x equal to 10 means? X equals 10 means that we construct directly the road from S to H. Since the domain of our function is a closed interval, so take note that this function here is continuous on the closed interval 0 to 10. So therefore, we can apply closed interval method to find the absolute minimum of this function. And we can also apply actually the first or second derivative test to find the value of x that will minimize this function. Let us now find critical numbers for this function because both maximum and minimum principles require us to find the critical numbers. So we have to compute for the derivative of this function here with respect to x. And the derivative will be equal to, of course, this will be 100,000 times the derivative of this, which is -1. So that is -100,000. And then plus, we just copy this constant factor here, 300,000 times the derivative of this. We apply extended power rule. We bring down the power. Subtract 1 from the power, so that is 1 half minus 1, so that is -1 half times the derivative of this base here, which is equal to 2x. And we can cancel here the 2 and then this 2, and we can factor out the negative 100,000. Again, the goal here is to easily find the critical numbers later. So we factor out the negative 100,000 and we'll get here positive 1 and then you'll get minus 3x over, this is written in radical form, the square root of 25 plus x squared. Now, this c prime of x, because of course the denominator will never be equal to 0 because x squared is always greater than or equal to 0. So the only critical numbers of this function c here is what? Okay, the values of x that will make this equal to 0. And this is equal to 0 if this is equal to 1. So therefore, we have here 1 equal to that expression, and then we cross multiply, we'll get this expression, and square both sides, we'll get 25 plus x squared equal to 9x squared, and then we'll get here 9x squared minus x squared, you'll get 8x squared equal to 25, dividing both sides by 8, and then taking square root of both sides, we'll get x equal to 5 over 2 square root of 2. So here you can already use the closed interval method to determine the x value that gives you the minimum cost. All you need to do is to find the value of this c at these x values at the endpoints 0 and at 10, and then at this critical value and compare the function values. Okay, so but we can also apply second derivative test here to determine whether this critical number, which is the only critical number of this function, so if this gives us the local minimum, then we are sure it's the absolute minimum of this function c, because it's the only critical number of c. So if we're going to apply second derivative test, we have to compute for the second derivative of this function. So the derivative of this one is equal to 0. And for the derivative of this second term, we use derivative of a product. So we'll get here, so we think of this one as a product of this expression times 300,000x. Okay, because 2 times 1/2 is just 1. So using derivative of a product, it will be equal to this expression times the derivative of 300,000x with respect to x. So that is 300,000. And then plus 300,000x times the derivative of this expression. So again, that is equal to, bring down the power, negative 1/2, subtract 1 from the power, so that is negative 3/2, and then times the derivative of the base, which is equal to 2x. And we can write this down in this form, okay, making the powers positive. And then when we factor out this expression, 300,000 over 25 plus x squared raised to 3/2, then we can write the remaining factors as 25 plus x squared and then minus x squared. Now, as you can see from this one, x squared minus x squared is just equal to 0. So therefore, the c double prime here, the second derivative, is always greater than 0. Okay, so since the value of the derivative of this critical number is equal to 0 in this case, and the second derivative is positive, so by second derivative test, we have a local minimum. But since this is the only critical number of the function, this local minimum is an absolute minimum. So therefore, this value here, function value, is the minimum cost. And what are we looking for? We're looking for the what? Number of miles that we have to use for this old road. Okay, so therefore our final answer will be the construction cost is minimized when this 10 minus x, so we found already the x, so that is 10 minus 5 over 2 square root of 2. This is approximately equal to 8.23 miles of the old road is restored. So therefore, we need to restore here 8.23 miles and then construct a new road from that point to the hospital to obtain the minimum construction cost. I hope you enjoyed this video. Please don't forget to like, share, and subscribe to help me grow this channel. Thanks for watching, and I'll see you next time. Bye bye.